So let's start with the theoretical background. To study and understand the behavior of dynamic systems, the easiest way is to analyze a single degree of freedom system, consisting a mass, a spring, and a dashpot. This might be familiar from our former webinar presenting the natural vibrations and response spectrum analysis. The partial differential equation is similar for both force and support excitations. We have inertia, damping, and spring forces balancing the external excitation on the right-hand side. This excitation is the dynamic loading, which is described as a function of time. There are many classification methods for dynamic loads. One of the classification aspects, for example, is if they are deterministic or non-deterministic. If the magnitude, position, and direction of the load and the variation of the load with respect to the time are known, the loading is said to be deterministic, and the analysis of a system to such loads is defined as deterministic analysis. Sometimes we find deterministic description of various stochastic loads in standards, such as blast loads or pedestrian walking or running loads. These functions are constructed to keep the design as simple as possible. If the variation of load is not known as a function of time, the loading is random or stochastic, and the analysis is then called non-deterministic analysis. Another important aspect is if the dynamic load is moving, such as a vehicle or a pedestrian load, or it's stationary. For the latter, the machine-induced load is a good example. The most important classification considers the form of the loading, whether it has a periodic behavior or not. The most simple dynamic loading is the simple harmonic excitation. Typically, machine-induced vibration can be described with this behavior. There are also more complex but still periodic loads, such as pedestrian walking loads. Among non-periodic loads, we have short-duration loads, for example an impulse or a blast load. Or we have long-duration non-periodic loads, for which the earthquake load is a typical example. The form of the dynamic loading is of great importance, since this determines whether we can obtain analytical solution or we have to use numerical methods to get the approximate solution of the differential equation of motion. First, let's talk about linear systems. The linearity requirements applies to geometric, material, and damping linearity as well. In case of linear systems, analytical methods and superposition can be used, which simplifies some scientific problems. Harmonic excitations are relatively easy to solve. We can use analytical solution for single degree of freedom systems. If the dynamic load is a general periodic excitation, we can apply Fourier transform to determine the harmonic components of the load to reduce the problem to a harmonic excitation problem. In case of non-periodic loads, such as an earthquake, spectral analysis is often used to determine the response of an ASDOF system. Please note that the spectrum shows the maximal responses of an ASDOF system calculated earlier with time integration methods. The analytical and spectral analysis of linear Amdahl systems are utilizing superposition to decompose the Amdahl system into separate ASDOF systems. Modal superposition gives us an approximate solution, since the accuracy depends on the number of natural vibration modes used for the analysis. Moreover, spectral analysis provides conservative envelope results, since the analysis is done in the frequency domain and therefore only peak results are superposed. As the diagram shows, time integration methods can be used for all cases. Time history analysis provides results in the time domain, therefore we obtain simultaneous internal forces, displacements, velocities, and accelerations in each time step, leading to less conservative results than in case of a spectral analysis. In case of linear systems, the combination of time integration methods with modal decomposition is a very powerful tool to solve huge Amdahl systems. In this case, however, the number of used natural vibration modes has a great impact on the accuracy of the results as mentioned earlier. If we have a nonlinear system, superposition cannot be used anymore. The only option to solve the equation of motion is the application of numerical time integration methods. A quick summary. Time integration methods or time history analysis can be applied for all types of loads, for example, arbitrary dynamic loads, and also for linear and nonlinear systems. For linear Amdahl systems, it is possible to combine time history with modal decomposition. Time integration methods have in common that the loading and the response history are discretized into a sequence of time steps, so we obtain simultaneous internal forces, accelerations, velocities, and displacements in the time domain. However, the most important thing about time history analysis is that it's the only method to solve nonlinear systems or systems with transient loadings. But what exactly is a time integration method? For a general inelastic Esdov system, the equation of motion can be described as follows with initial conditions shown on the right side. The applied force is given by a set of discrete values as well as time steps and time interval. The time interval is usually taken to be constant, but this is not necessary. The response is determined at discrete time instant ti, then a numerical procedure enables us to determine the responses at the next time instant ti plus 1, satisfying the current equation of motion. When applied successively, the time-stepping procedure gives the desired responses at all time instants. The non-initial condition provides the information necessary to start the procedure. Stepping between the time instants is the key feature of each time integration method. Independently from the chosen method, there are some basic requirements that should be met. Convergence. As the time step decreases, the numerical solution should approach the exact solution. Stability. The numerical solution should be stable in the presence of numerical round of errors, which are always present in case of computer calculations. Accuracy. The numerical procedure should provide results that are close enough to the exact solutions. All these properties are highly influenced by the chosen integration time step. The most used time integration types regarding the approach used in the algorithms are methods based on interpolation of the excitation function, based on finite difference expression of the velocity and acceleration, or they are based on assumed variation of accelerations. Apart from the approach the particular method is based on, the methods can be classified in several ways. Usually, step-by-step integration methods are classified as either one-step or multi-step method, and whether it is an explicit or an implicit method. In case of explicit methods, the calculated responses in a time step only depend on the response values obtained in preceding steps. There are no coupling conditions between the new response values. An implicit method is much more complicated. New responses are obtained by solving a system of coupled equations, and the equations contain also responses calculated in the same current time step. The color code indicates if the method is unconditionally or just conditionally stable. Remember that stability means that truncation errors do not cause unstable, for example, constantly increasing responses. Unconditional stability means that the time step can be chosen freely. It doesn't affect the stability of the system. Of course, the time step influences the accuracy of the responses, so it should be carefully set to obtain accurate results. Note that explicit methods are always conditionally stable. Some implicit methods, for example the Newmark beta method or the Wilson theta method, are either unconditionally or conditionally stable depending on the chosen parameters. Explicit methods are faster to solve, but due to their conditional stability, the time step has to be often much smaller than in case of implicit solvers, which has a counter effect on the efficiency. In this webinar, only the Newmark beta method is presented in detail, since this method is widely used by many software packages and also implemented in AxisVM. The Newmark beta method is very attractive because depending on the chosen parameters, it can be turned into unconditionally stable implicit method, conditionally stable implicit method, or conditionally stable explicit method. The Newmark beta method is a method based on assumed variation of acceleration, where the f and g functions control the stability and accuracy of the solution. Based on this assumed variation of acceleration, we can define the velocity and displacement of the current time step using two parameters, gamma and beta. Now, we can rearrange the equation for the displacement and express the acceleration. With this term, we can also redefine or rearrange the velocity to eliminate cross-dependency between the different response components. Now, both the acceleration and velocity are expressed with responses from the previous step, and they are only dependent on the displacement responses of the current step. Substituting all components into the differential equation of motions and rearranging some elements, we obtain the modified stiffness matrix and modified load vector, which is the basis form of the Newmark beta method. In general form, the Newmark-Beta method is an implicit method, since the equation of motion has to be solved in the current time step, considering not only previous, but the current response values as well. As already mentioned, stability is an essential requirement an integration method has to fulfill. The stability depends on the chosen parameters and the time step. Several methods exist to study the stability properties, like the method proposed by von Neumann. This method consists in expanding the solution in a finite Fourier series and checking for growing unstable solutions by analyzing the behavior of the so-called propagation matrix during free vibration of the dynamic system. The propagation matrix is a transformation matrix of the responses between each time step. If we have a series of time steps, this propagation matrix is multiplied by itself many times. The propagation matrix of the power of n can be described with eigendecomposition, where P contains the eigenvectors and J diagonal matrix represents the eigenvalues of the propagation matrix. From this form, it is obvious that the propagation matrix is not constantly increasing, only if the spectral radius, therefore the maximal absolute value of the eigenvectors, is smaller than 1. The propagation matrix of damped systems under free vibration looks like this for the Newmark-Beta method. It can be shown that all variants of the Newmark-Beta methods are unconditionally stable if the criteria on the left side are fulfilled. If only the first criterion is satisfied, we get a conditionally stable method, where the time step should be chosen carefully and should be under the critical time step to avoid instability. If the gamma and beta parameters are chosen freely and they do not meet the first two requirements, the method can become unstable, leading to false results. Typical parameters for unconditionally stable solutions are gamma 0.5 and beta 0.25, which is the average acceleration method. Two other conditionally stable methods are often used, namely the linear acceleration and the central difference method, which is basically an explicit solution setting beta to 0. Let's analyze these methods in detail. In the following figures, the spectral radius of the propagation matrix is plotted as the function of the damping ratio and the time step related to the natural frequency of the system. Using the average acceleration method leads to unconditionally stable process. The spectral radius never exceeds 1, the system remains stable whatever time step is used. Please note, however, that the accuracy is highly influenced by the chosen time step, so it should be chosen with care. The linear acceleration and the explicit central difference method are only conditionally stable. The spectral radius increases rapidly if the critical time step is reached. Note also that the spectral radius is dependent on the damping, but the critical time step is not. In case of conditional stability, the highest relevant natural frequency of the system is of high importance, since it defines the minimum time step that should be used to achieve stability. In axis VM, the unconditionally stable average acceleration method is implemented due to its robustness, stability, and accuracy. The two most important errors that are introduced by time integration methods are numerical damping and elongation. The amount of errors are influenced by the parameters of the method and by the time step size. Numerical damping is controlled by the gamma parameter. In this figure, we see the free vibration responses of an undamped system. We can observe amplitude decay at increasing gamma and beta parameters, despite the fact that the response should reflect the vibration of an undamped system. This is called numerical damping, which can strongly underestimate the responses. Generally, the average acceleration method provides the most robust results without any or significant numerical damping. The other typical numerical error is the period elongation. The figure shows the results of a free vibration using the average acceleration method with different time steps. The influence of the time step size on the period elongation is clearly visible. Interestingly, 10 time steps per vibration period is usually recommended to obtain reliable results in literature. In general, 20 to 50 time steps are suggested to be used. If it is possible, the most reliable way is to carry out a convergence study by repeating the analysis using even smaller time steps and comparing the results to make sure that no error is introduced in the analysis. In this table, the stability limits and different types of errors of some frequently used Newmark methods are resumed. The periodicity error is quantified by the ratio of the period elongation and the natural period of the system. On one hand, the linear acceleration method gives the smallest elongation error, but on the other hand, this method is only conditionally stable. Choosing a sufficiently small time step makes the average acceleration method one of the best among all, since it is unconditionally stable and has no amplitude error at all. Once again, we have to emphasize that great care should be taken at choosing the right method parameters, and time step size for a specific problem. As mentioned earlier, convergence studies can help to identify step sizes with acceptable accuracy. Also, it is always a good idea to monitor the evolution of the energy during the transient dynamic analysis, which is especially important in case of nonlinear problems to detect the beginning of instabilities. Before we finish our overview about the theoretical background, one topic should be briefly discussed: the damping of the system. There are many formulations for the damping matrix, but the most often used and most easily programmable is the mass and stiffness matrix proportional Rayleigh damping. The Rayleigh damping coefficients control the proportion of the mass and stiffness matrix, and they should be calculated from the damped frequency range and the damping ratio according to this figure. Since it is a two-parameter description of the damping, care should be taken choosing the relevant frequencies. Rayleigh damping underestimates damping between the chosen frequencies and overestimates it at lower and higher modes. For this reason, in most of the cases, the frequencies should represent the lowest and highest dominant frequency of the analyzed system.
In this section, we will shortly introduce the possibilities of time history analysis in AXIS-VM. Let's start with an overview of the AXIS-VM packages. Let's see what we need in order to be able to carry out time history analysis. At the moment, AXIS-VM provides 4 modules for dynamic analysis, such as SE1 for response spectrum, SE2 for pushover, DIN module for time history, and FFA module for footfall analysis. In this webinar, we will focus on the DIN module for time history analysis. This table below presents the different packages using only beams or also surface elements, and with a great variety of analysis methods from linear static and vibrations through buckling and plastic nonlinear solvers. The basic package is actually sufficient for linear time history analysis, but PNL 1 or 3 is needed for nonlinear problems. In the case of dynamic analysis, the program determines the displacements and the internal forces of the structure for each time step, corresponding to the defined dynamic loads. The analysis can be carried out by considering linear or nonlinear material behavior, or also geometric nonlinearity. The following dynamic actions can be applied: dynamic point load acting on a node, domain, or load panel, distributed surface load on a domain or load panel, node or nodal support acceleration. It is important that the DIN module is independent from any design codes or standards. So the summary of the main characteristics are that the time integration is carried out by the Newmark beta implicit numerical method, geometric and material nonlinearity can be taken into account, the dynamic load functions can be defined by either numerical data at sampling points or by analytical functions, the intermediate points of the load function can be determined with linear or Whittaker-Shannon interpolation, the accelegrams can be corrected in order to obtain zero end speed and displacements, and that the internal forces can be used in standardized design procedures. In the dynamic analysis, a static and a dynamic load case can be considered. The results are stored at every time step or at specified time steps. In addition, the correction of the load function and the interpolation method, as well as the nonlinearity and convergence criteria, can be set. Movement of a specific node, for example displacement, velocity or acceleration, can be monitored during analysis, which can reveal certain structural behavior or instabilities. If the sampling points of the load function are not coinciding with the time steps, the program interpolates the function value at a given instance of time with linear interpolation or with Whittaker-Shannon formula. The latter can approximate a continuous function, which is better discretized with uniform time steps. The real or generated seismic records can be modified. Due to measurement error, the recorded acceleration data may not result in zero end speed. The applied algorithm modifies the original acceleration in order to obtain zero end velocity and zero end displacement. The structural damping is taken into account using proportional Rayleigh damping. Nodal damping can be taken into account with spring and dashpot elements. Bilinear characteristic can be considered according to the Maxwell or Kelvin model. The computed kinematic results like displacements, velocities, accelerations, and internal forces and moments can be plotted as a function of time or as a function of any other time-dependent results. Animations can be displayed for time-dependent changes of any result component and can be saved as a GIF or AVI file type. The speed of replay can be adjusted and arbitrary subdomains can be chosen for the animation. Most of the features will be presented through some examples in the next sections.
In the first example, we will carry out the seismic analysis of a typical reinforced concrete girder bridge using response spectrum and time history analysis. We will consider only the longitudinal behavior. The bridge has 5 spans with 35 meters each and pier height of 15 meters. We have a rectangular pier section and a box section for the deck. Rigid supports are assumed at the pier feet, while the abutments provide only vertical and transversal support. The deck is connected to the pier through spring elements, modeling the bearings of the bridge, and rigid elements are used to account for the eccentricity of the deck. The deck is fixed in the longitudinal direction only at the third pier to provide free movements of the bridge during thermal expansion or contraction. This means, however, that only one pier has to take all the longitudinal forces caused by an earthquake. Now we go to the Load tab and define the load cases and loads. For dynamic analysis, we need to construct the mass matrix, so permanent loads are essential. Under permanent loads, we have the structure weight and we neglect the weight of any vehicle on the bridge. For the seismic analysis, we have the response spectrum load case, which has its own load group and therefore can be combined automatically with other actions to carry out design checks. The spectrum has type 1 shape with ground type C according to Eurocode, and the P ground acceleration is 1 meter per square second. The dynamic loads for time history analysis have a special ungrouped load case. The results will only be available in the dynamic module and cannot be combined automatically with other load cases. As mentioned earlier, we can apply dynamic point load on a node, domain, or load panel, distributed surface load on domain or load panel, and node or nodal support acceleration. The seismic effect is a support excitation defined as a series of acceleration values called the seismic record. We set the longitudinal acceleration to 1 meter per square second and we select the dynamic load function describing the change of amplitude as a function of time. In the load function editor, we can add or edit dynamic load functions. We can define the time series with mathematical functions, where we can set the sampling time step and also the maximal duration. This option is useful if the load function is harmonic, or can be easily described with mathematical functions. Since the seismic record is an arbitrary loading, we have to provide the amplitude values in a tabulated form. We can also open predefined records from our library, where we can save new ones as well. In our example, we use an artificial seismic record matched to the chosen response spectrum. Such artificial records are allowed by Eurocode as long as they follow closely the standard response spectrum. The load tables can be copied, imported, and exported, and also added to the report as well as the load function diagram. There are two really useful options in AXIS-VM to modify the use load functions. The first one is the resampling of the dynamic load function. The values of the new function at sampling instance locating between the original points is obtained by interpolation. With resampling, we can manipulate the density of data points, and also we can restructurize the time steps to get equivalent time step durations. We can use piecewise linear interpolation or the Whittaker-Shannon algorithm, which uses continuous function to capture extreme values in case of rapid sign changes. In some cases, measured or generated accelerations do not produce exactly zero velocity and zero displacement at the end of the record because of inaccuracies and numerical errors. The non-zero final velocity appears as an infinite motion of the supports with constant velocity beyond the end of the record. The non-zero final displacement causes that the supports stop out of their original position at the end of the record. Any of these inaccuracies can be eliminated by applying a small modification to the acceleration record. We already did this correction, so we go back and choose the corrected artificial record as our dynamic load function. For the dynamic analysis, the proper mesh size is of high importance. On the mesh tab, we set a mesh size of 2.5 meter for all beam elements. Before we carry out the response spectrum analysis, natural frequencies of the structure must be determined. In the vibration module, we can set the parameters for the linear vibration analysis. The mass matrix is constructed using the structure weight of the bridge. We want to obtain 10 mode shapes, and we consider only the mass components in the longitudinal direction. As mentioned earlier, for simplicity, we do the analysis only in this direction. Now let's check the calculated vibration results. The first dominant mode shape is the vibration of the deck with the one pier fixed to it. The modal mass factor is not 100%, but basically it represents the whole moving mass of the deck fixed pier system. The longitudinal behavior can be described with an SDOF system, where the mass is basically the mass of the deck and the spring is provided by the horizontal stiffness of the pier, calculated at the height of the deck. The other mode shapes are the different vibration modes of the other three piers, but they have no influence on the global longitudinal seismic behavior. They could be simply modeled as independent cantilevers. The dominant vibration modes can be found in the tabulated results. We have two dominant frequencies to consider later on: 0.7 Hz and 4.1 Hz, associated with the pier deck system and the freestanding piers respectively. Now we can conduct the response spectrum analysis by starting the linear static analysis on the static tab. To save some time here, we are presenting the model with calculated results. From the bending moment results, we can see that the most loaded pier is the one connected to the deck. The others are only lightly loaded from their own vibration. First, we check the longitudinal bearing force, and then the base shear force as the reaction force at the pier foot. We can see that the maximal longitudinal bearing force is only 5% smaller than the maximal base shear force at the bottom of the bridge. This shows that including the weight of the pier just slightly changes the total base shear force. The mass of the vibrating system is mostly provided by the deck. Now, let's go to the Dynamic tab to carry out the time history analysis. We can apply a static load case along the dynamic load to consider gravitational loads and permanent loads present during the vibration. This is important, for example, in case of a reinforced concrete column, since we need the normal force level for the design check. We select our predefined dynamic load case. If the time increment is chosen lower than the sampling of the record, interpolation has to be used to get intermediate data points. We use the Whittaker-Shannon interpolation to get acceptably accurate results. The total time is the length of the record, or we can set a longer total time as well. In this case, the load function becomes 0 after the seismic record, and the system is analyzed in free vibration. We can track the behavior of one node during the calculation, which can help to identify if the analysis becomes unstable. In this case, we can easily stop the analysis to check the model, the calculation parameters, and to start a new analysis without having to wait for the current calculation to be finished. The frequency domain we have to consider for Rayleigh damping is the two dominant natural frequencies, which are 0.7 Hz and 4.1 Hz. Based on these values, the coefficients can be determined with the formula showed in the theoretical background presentation, considering a damping of 5%. We can choose if we want to save all time steps or just at regular intervals. The latter can reduce the result file size. However, important information such as extreme values may not be cached in the post-processing. If we forgot to correct our record, it can be still done before the analysis. The mass matrix is constructed either from load cases or combinations, or directly from nodal masses and element masses. Conversion from and to each other is also possible. The mass matrix type is diagonal to maintain the efficiency of the solver. We can consider material and element nonlinearity, such as tension-only braces, plastic material models, yielding hinges, and so on. Moreover, we can add second-order effects by considering geometric nonlinearity. This can be useful if the second-order sensibility of the structure is high and cannot be taken into account with simplified methods. Convergence criteria and iteration control are used only in case of nonlinear analysis. After setting all parameters, we can start the calculation. We already carried out the analysis, so we can go directly to the results. From the drop-down menu, we can select each time step or the envelope results. The time history analysis provides us the dynamic displacement, velocities, accelerations, internal forces, stresses, spring forces, and so on. Let's select the beam bending moments in the longitudinal direction. The bending moments of the fixed pier just slightly differ from the ones obtained with response spectrum analysis. This is due to the fact that the seismic record is matched to the spectrum, and also that the seismic behavior can be characterized with an S-stop system for which the response spectrum provides the exact extreme results. In case of freestanding piers, a similar behavior can be observed, but the time history results are more favorable. Using the diagram display, we can plot the result series as a function of many parameters. We can plot maximum 2 diagrams, where the x-axis is not necessarily the time. Here we plotted the longitudinal acceleration of the deck and the bending moments in the fixed pier as a function of time. The two values are clearly coupled, showing that the system has a behavior of an S-stop system. Also, we can see the natural frequency of the deck pier system, described with a natural period of about 1.4 seconds. We can set same ranges on the axis, but only if the units are identical. We can also set the range of the plot to get a better and detailed view of the results. In the next step, we will analyze the bridge with nonlinear behavior. In our example, the fixed pier capacity is not sufficient for such large bending moments. Assuming that this is an existing bridge, seismic mitigation methods can be effectively used to reduce the seismic actions on the pier. We will use an isolator on top of the pier to partially decouple the movements of the deck and the pier. Axis VM provides isolator elements, such as rubber isolator, curved service slider, or user-defined isolators. They can be found and set among spring elements. The nonlinearity of isolators are introduced through a bilinear behavior. We can set the initial and post-yield stiffness as well as the maximum force at the yielding point. For rubber isolators, we have to define the vertical stiffness, and for all isolator types, we need the ultimate deformation capacity for the design and for the iteration procedure in case of equivalent linear analysis. The isolator elements are considered in different ways depending on the analysis method. The initial stiffness is applied in case of buckling analysis. For linear, static or dynamic, and for vibration analysis, the effective or secant stiffness is used. This effective stiffness is determined by running an internal iteration to find the compatible forces and deformations of the isolator. The real plastic behavior is utilized in pushover and nonlinear dynamic analysis. We use a simple rubber isolator in this example, and we carry out again the vibration and static analysis, where the effective stiffness of the isolator is used. The stiffness reduction is obvious from the model analysis. The natural frequency dropped from 0.7 Hz to 0.3 Hz. The application of isolator is apparent also in case of equivalent linear response spectrum analysis. The bending moments and bearing shear forces are drastically reduced. Now we set the dynamic analysis parameters and carry out the nonlinear time history analysis to consider the plastic hysteretic behavior of the isolator. We don't change the calculation parameters, but we activate the nonlinear behavior and we set the convergence criteria for accurate results. Once again, we calculated the results earlier, so we can go directly to the postprocessor. If we scroll down to the envelope results, we can see that the bending moments are even lower than in case of the equivalent linear response spectrum analysis. We can quickly compare the two by swapping between the static and dynamic tabs. The nonlinear time history analysis considers the real plastic hysteretic behavior and energy absorption of the isolator and leads to more favorable results. Nonetheless, the iterative response spectrum analysis using isolator elements in AXIS-VM can provide reliable and conservative results for a preliminary design. Plotting again the displacements of the deck and the bending moments of the pier as a function of time, we can observe the huge effect of the isolator on the seismic behavior. The movements of the deck and the pier are decoupled. The system doesn't act like an SDOF system anymore. Let's plot the isolator forces versus the isolator deformations. First, we select the spring deformation from the menu and we select the node we want to display. As a Y component, we set the spring force and again select the isolator spring. Once we are done, the plotted diagram shows the plastic hysteretic behavior. This behavior can help to further reduce the seismic actions on the pier through energy dissipation. An animation here is also created. So let's see the two behaviors, the linear and the nonlinear results using an isolator, parallel to each other as a closure of the first example.
The second example is a 2D steel frame. On this frame, we have two machines installed on the first floor, causing harmonical loading due to the eccentric rotation, while the beams are connected to the columns through hinges, and the column feet are also applied with hinge supports, and the lateral stiffness and stability is provided by the bracing elements, which have nonlinear behavior, so they can be loaded only under tension. In this example, we defined the permanent loads as nodal masses. We have applied two dynamic load cases, one for the linear and one for the nonlinear analysis. The same model with the same dynamic loading can be analyzed with different calculation parameters, but for each calculation case, a separated load case has to be defined. The eccentric rotating weight of the machine causes rotational harmonic forces, which can be modeled with a horizontal and a vertical component. Horizontal component is characterized with a sine, while the vertical component with a cosine function. However, this applies only to the steady-state excitation, where we have a pure harmonic motion. During the start and stop phases, the machines are accelerated or deaccelerated, where the angular frequency of the rotating eccentric weight is increasing or decreasing. The centripetal force is the function of the square angular frequency, which makes the start and stop phase a complex loading scenario. This start-stop phase can be very important in the dynamic analysis. Even if the operational excitation frequency of the machine is far away from the natural frequency of the structure, often the structure is undertuned, meaning that during acceleration or deacceleration, the frequency of the machine will catch the natural frequency of the structure for a short period of time. This leads to an instant resonance and to an impulse force causing high amplitude vibrations. This vibration, however, is a free vibration and will decrease over time through structural damping. After some time, the vibration is stabilized and we get the pure steady-state vibration of the system controlled by the external excitation. The start and stop phase can be defined only with integration, so it is calculated externally and imported in a tabulated form. Since the stop phase has a similar effect as the start phase, the latter is not modeled to get a long period of stable, steady-state excitation and solution. The excitation has a frequency of 3 Hz and an amplitude of 20 kN. Here again, a proper mesh size is essential to get accurate results, and in this example, each beam element is divided into 4 pieces. To evaluate the basic dynamic behavior and to determine the dominant mode shapes for the Rayleigh damping coefficients, we carry out the vibration analysis. The first mode shape characterizes the horizontal vibration with a high modal mass factor, showing that this is the first dominant mode shape to consider. The first mode shape has 2 Hz, while the excitation frequency is 3 Hz, so the structure is undertuned, and during start and stop phase the excitation frequency will reach the natural frequency of the structure, therefore it will cause a temporary resonance. If we check the tabulated results, we can get the range of interest for the Rayleigh damping coefficients. Now we go to the Dynamic tab and we will carry out the time history analysis. We choose the first dynamic load case, set the time increment and total time, and set the Rayleigh damping coefficients based on the 2 dominant natural frequencies. We do not define static loads, we use the element masses and nodal masses instead to construct the mass matrix. Also, we do not need the permanent loads since we are interested in the internal forces caused only by the machine excitation. These settings are useful if you want to get the stress ranges for fatigue checks, avoiding the need to eliminate the stresses caused by permanent loads. At first, we don't consider nonlinearity and we can start the analysis. The results are already calculated, so we can jump right into them. Let's check the displacements near the machines first. To do this, we go to the Diagram Display tab and select the node near the left machine for evaluation. The results clearly show that we have relatively high amplitude vibration as we accelerate the machine. After that, the free vibration is decreasing due to the structural damping. At the end, we get pure and stable forced vibration solution, where the responses are controlled by the external excitation. If we narrow down the plot range, we can have a better overview about the steady-state solution. We can easily get the results for the accelerations as well. The accelerations can be used to evaluate the structure and to determine if the vibrations are causing uncomfort to the people inside. For example, as per ISO 2631, we can determine the maximal allowed human exposure time, or we can check if the limit of a given exposure time is exceeded and the structure fulfills the requirements or not. Now let's plot the X and Z displacements on the horizontal and vertical axis. We have to select the same node to define the horizontal displacements on the X and the vertical displacements on the Y axis. At first glance, it looks like a chaotic diagram, but let's adjust the range to plot the line from the beginning. As we can see, the rotation movement caused by the machine is increasing like a spiral, then gets chaotic as we reach the natural frequency of the structure. After that, the movements are stabilized and we get an elliptical curve, which is a typical response to a harmonic excitation. Last but not least, we plot the bracing normal forces on the opposite sides. We set again the time on the horizontal axis and we activate the second diagram to be able to select both of the bracings. We select the braces at the bottom on the left and then on the right side as well. Again, we can observe the temporary resonance at the start phase and the steady-state stable vibration after the free vibration is damped. The braces are activated symmetrically. One brace is under compression and the other is in tension. In case of fatigue checks, we are more interested in the steady-state solution than in the maximal response at the start phase. The latter can be used for structural checks, but the number of start and stop cycles of the machine is orders of magnitude smaller than the millions of cycles during the steady-state operation. If you want to see the results for all elements, but you want to see only the steady-state part, we can create envelopes of the results. We go to the Display Parameters menu and then to the Envelope tab. Here we can add a new envelope and select which time steps we want to see in the envelope. We created two envelopes here, one for the linear and one for the non-linear steady-state solution. In both cases, we use the last 2 seconds of the time history results. Now let's scroll down and select the steady-state envelope for the linear analysis. And from the result components, we choose the normal stresses to be plotted. This way, the stress ranges for fatigue checks can easily be assessed. Now let's see the nonlinear analysis. We go to the Dynamic Analysis menu and we choose the second load case created for the nonlinear analysis. It is important to mention that the program keeps the previous results associated with previous load cases, so we can carry out dynamic analysis one by one, and we will have them all in the result file as well as in the post-processor. We keep the same parameters as in the case of linear analysis, but now we consider nonlinearities as well. Remember, we have tension-only truss elements in the system, the braces. We set also the convergence criteria to get stable and accurate results. After setting the parameters, the analysis can be started. Since we already have the results, we can jump back to the postprocessor. We select the nonlinear time history results, and we can plot again the normal forces in the braces. As we can see here, the nonlinear solver provides us the required results. The braces can take only tension forces. The right and left braces are alternately loaded. The behavior here is similar like in the case of linear solution, but with slightly higher internal forces. Even if we have only one active brace in one direction, the force is not doubled. The reason is that in the case of a nonlinear system, the stiffness changes during the vibration, and this stiffness change has an effect on the response. In our case, the smaller stiffness brings the natural frequency even further away from the excitation frequency, leading to smaller global responses, which on the other hand is distributed just on one activated brace. This shows that the dynamic behavior of nonlinear systems are really hard to estimate, where the nonlinear time history analysis can be a really powerful tool. We can plot also the stresses of the beam elements. If we choose again our truss elements representing the braces, we can get the stress time history for these members. This shows clearly that we have a pulsating stress range, and again we can use the steady state part for fatigue assessment. Now let's select a beam element. We can select also the internal mesh nodes to display the results. In case of beam element, we have stress results in all the defined stress points of the cross-section. The program shows the cross-section and numbering as well. From the drop-down menu, we can select which stress point should be plotted. We can obtain the results also in a tabulated form, which we can export or add to our report. Since we are interested in the steady-state solution, here we also created an envelope result view considering only the last couple of seconds. Let's scroll down and select again the envelope normal stress results from the nonlinear time history analysis. We can check the stress ranges and easily compare them to the linear solution in one model. We can also compare the maximum accelerations by changing the display between the linear and the nonlinear solutions. With that, we have reached the end of the presentation. We hope that with these two examples we could show how efficiently we can tackle linear and nonlinear dynamic problems with AXIS-VM.